Hello everyone, my name is Chen Hui from Chalmers University of Technology. The topic of this presentation is misspecified Kramer bound-based performance analysis of 6G localization on the hardware impairments. Let's first start with the motivation of this work. The communication systems beyond 100 GHz are likely to be more affected by hardware impairments, and the hardware impairments are likely to be more problematic for localization and sensing rather than for communication. More specifically, communication cares about the end-to-end channel. However, from the localization and sensing perspective, geometric information in the channel matters. The questions we want to answer are as follows. What are the relevant hardware impairments and how to model them? How do different types of impairments degrade localization? How to translate localization performance loss into impairment requirements? And do we need novel methods for hardware impairment mitigation for localization and sensing? In this work, we will answer the first three questions by providing a system model with hardware impairments and MCRB analysis. A widely used far-field MIMO model without impairment using a single F-chain can be formulated as follows. The received signal symbol at the teeth transmission, kth subcarrier, is the multiplication of a combiner at the receiver, the channel matrix, the precoder at the transmitter, and the transmitted signal plus noise. Due to the sparsity of the channel at high frequency, we can use limited channel parameters to represent the whole channel matrix. In other words, from the channel matrix, we can extract the complex channel gain, direction of arrival, direction of departure, delay, and the velocity of each path. From those estimated channel parameters, we can then estimate UE states, including position, orientation, clock offset, and velocity for localization, and estimate instance point states, including position and velocity, for sensing purposes. When hardware impairments are considered, the signal model becomes more complicated. The transmitted signal will be affected by the IQ imbalance, phase noise, and carrier frequency offset, and power amplifier nonlinearity. The channel will be affected by the array response error and array geometry error. The receiver signal will be affected by mutual coupling and also phase noise, CFO, and IQ imbalance. We have prioritized the mentioned impairments, and in this work, we focus on the first four, which are phase noise, CFO, mutual coupling, and power amplifier. For each type of impairment, we assume a mismatched model and a true model. The true model considers all the impairments, while the mismatched model has a practical assumption that not all the impairments information is available. More specifically, the residual noise and power amplifier nonlinearity are not known. When modeling the impairments, some of them are randomized, while some of them are fixed. The residual phase noise will change from sample to sample. The residual CFO varies from block to block. The rest of the impairments are different across different devices. With the help of MCRB, we are able to obtain the localization lower bound of a mismatched model, processing true model observations. The model is said to be mismatched when the true model, where the observations are obtained, and the model from which the estimation algorithms are derived, are different. In this case, we can use MCRB to find the lower bound of the mismatched model with three steps. First, find the pseudo-true parameters to minimize the Kullback-Leibler divergence as equation 22. Then obtain two possible generalizations of the theme with respect to the pseudo-true parameter, matrix A and matrix B. Third, obtain the lower bound of the mismatched estimator with respect to the real parameters from equation 20. In the simulation, we consider a simplified uplink scenario with synchronization. where the base station is equipped with a uniform linear array and the UE has only one antenna. The assumptions of single antenna UE, perfect synchronization, and pure line of sight may not be realistic in practice, but it's an initial step to analyze and understand the effect of hardware impairments on localization and sensing. The phase noise and carrier frequency offset happen at both the transmitter and the receiver. Mutual coupling is considered at the receiver, and power amplifier nonlinearity happens only at the transmitter antenna. 3 channel parameters are involved, namely 1 complex channel gain, 1 direction of arrival, and 1 delay estimation. We use angle error bound, delay error bound, and position error bound obtained from CRB to indicate the localization performance. As for the simulation parameters, the carrier frequency is assumed to be 140 GHz. The bandwidth is set as 1 GHz. The rest of the parameters can be found in Table 1 of this paper. We consider 2 models here. Model 1 is a true model, considering all the impairments. Model 2 is a mismatched model, considering part of the impairments. We also adopt 2 estimators here. The mismatched maximum likelihood estimator uses Model 2 to process the data from Model 1. The maximum likelihood estimator uses the same model for data generation and processing. Comparison between estimator results and different lower bounds is shown in the red figure. Due to the impairments, the performance saturates when the transmission power exceeds 30 dBm. However, with the knowledge of the impairments, the bound, which is the red curve with square markers, could be lower than the lower bound, which is blue curve with circle markers. At low transmit powers, the lower bound and CRBs coincide, implying that the impairments are not the main source of error. At higher transmit power, after 20 dBm, lower bound deviates from the CRB, and the position performance is thus more severely affected by the impairments. The mismatched maximum likelihood estimator closely follows the lower bound, indicating the validity of the lower bound. In terms of the CRB M1, we observe the bound converges to a certain value after 30 dBm due to the power amplifier nonlinearity, while the CRB M2 keeps a fixed downward trend. To gain a deeper understanding, we study the impact of impairments on angle and delay estimation, considering different impairments separately. The results of phase noise, carrier frequency offset, mutual couplings, and power amplifier are shown in figures A to D. We perform multiple hardware realizations when the fixed parallel signal for A to C, and multiple parallel signal realizations for D. We can see that different types of impairments affect angle and delay estimation differently. The phase noise and power amplifier affect both angle and delay estimation. However, the effect of the power amplifier is mainly caused by the distortion of the parallel signals, whereas the effect of phase noise depends on the residual noise level. The CFO and mutual coupling have a more significant effect on angle estimation compared to delay estimation, since the CFO affects the phase changes across beams, and the mutual coupling distorts the steering vector. In addition, the CRB of Model 1 is close to the CRB of Model 2 within a reasonable level of impairments, as seen from figure A to C and in figure D when the power is smaller than 30 dBm. Since the localization performance depends on the angle error bound in terms of degree and delay error bound in terms of meter, we evaluate the localization performance as a function of the standard deviation of phase noise for different values of average transmission power using 100 realizations, which is shown in the red figure. The impairments produce a large perturbation in the high SNR scenarios. As for low SNR, the noise level is high enough, and the hardware impairments under a certain level will not degrade the position error bound too much. And similar patterns can be seen for carrier frequency offset and mutual coupling. To conclude, we modeled different types of impairments and utilized the MCRB to evaluate the error caused by model mismatch. The effects of residual phase noise, residual carrier frequency offset, residual mutual coupling, and power amplifier nonlinearity on angle and delay estimation are evaluated. From the simulation results, we found phase noise and power amplifier affect both angle and delay estimation, whereas carrier frequency offset and mutual coupling have a more significant effect on angle estimation. With perfect knowledge of the impairments, the bound of the true model is close to the bound of the mismatched model, but will saturate at a certain level in the high SNR regime due to the power amplifier nonlinearity. Regarding the future work, we want to compute MCRB for 3D position and 3D orientation scenarios to evaluate the effect of impairments on position and orientation estimation. We will also consider more types of impairments, such as a recalibration error, and evaluate the effect on localization under mobility, and obtain realistic impairment parameters from experimental measurements. Finally, we want to design impairment-tolerant payload signals and hardware impairments estimation and mitigation algorithms for accurate localization in 6G systems. That's all for this presentation. Thanks for your time, and I'm happy to answer all the questions.